I'm Shadi. I'm with Wolfram Research. I'm giving a talk about what's new in image and signal processing, and we have some more talks about image and signal processing. So basically, I think I'll be mentioning all of the things that have been added to Wolfram Language 11. In total, our team has 8 talks, including this one. So there are more specific talks. I'll try to leave the content that is being covered in those other talks to the specific talks. I'll try to mention them in the relevant slides. But then mainly, I'm going to mention the audio processing capabilities that have been added recently, signal processing, things that are new, image processing, a lot is new, a lot is coming, and then the integration with neural networks, which I know a lot of image processing applications is now being tried using the neural networks. It's great timing, great capabilities. So audio is new. The need for, we had a sound object since very early in Mathematica. However, combined with the combination of waveform, the sampled sound, as well as the symbolic sound was not super efficient. And then a lot of audio transformations and effects and so forth were not super efficient in that environment. Plus, that framework did not let us handle a lot of large audio signals or a large collection of audio signals. The introduction of audio is trying to separate those two worlds and stays focused on sampled audio data. And then now a WAV file that used to get imported as a sound object gets imported into Mathematica as an audio object. We have different views so that you can see more details or less details. It can be played. You can see a little waveform and so forth. There is support for different devices that can be chosen, which one you want to play it from and so forth. Functions like audio plot, and I think overall a collection of 50 or so new functions specific to the audio has been added to version 11. And then hundreds of functions got updated to work with the audio object. For instance, you can compute the spectrogram, do low-pass filtering to get rid of the noise and so forth. A lot is coming. One great addition that we have added to audio is that you can just specify a file path instead of the, and then you can just pass it to the audio. So audio can be can get created from the matrices, the array or a matrix for multi-channel audio object and gets created in memory. But if you give it just a file path, as you see, there is a file icon right here. It might be just a bit too small, and the file path specifying where to link to. The input form of this object is just a file path. The byte count of it is just a couple of 100 bytes. Some of the things that are really going to be covered in some other talks, so I didn't include it from the beginning. For a second of audio, 440 bytes only, and this is the key to allowing access to very large files. Hours of audio can be stored in the file, and you just store 440 bytes or so in the memory, and then it can be played. Nothing again is going to be imported to begin with, and it just gets streamed, and you can process it as it's being streamed into Mathematica. So the amount of memory that you're using at the same time is very limited, very low, very efficient. Well, based on your operation, it may or may not end up being real time. But as far as memory, it's very efficient anyways. And then in addition, we also have access to URL types of audio objects. So this particular implementation is downloading the audio from the URL, saving it, and then still you see the file path of the audio, a little new icon, separate icon there to specify this is not on your local file system, but as well can just be played back, streamed, again, nothing in the memory. This is all out of core. And then also you can imagine this is very useful if you have a larger collection of audio objects and you want to do some kind of an analysis on them and you don't have the memory to import all of that data into your computer, especially on something like this, which is not really very powerful. Now, what are the kinds of things that we can do with audio objects? As I said, there are a ton of other talks talking about details of things that can happen, but we can use the whole world of Wolfram language to create audio objects and to process audio objects. In this particular example, I'm just creating some random integers and then some time series and creating a sine wave based on the time series that its frequency is being changed with the function that I created with that time series. And this is just a random synthesized generated audio object. And then just as I said before, you can compute different things like spectrogram or additional built-in functions that we have added. You can compute locally measurements on your audio signal like the MFCC, which is the Mel frequency spectrum, used a lot for analyzing and comparing audio signals. And then what I'm doing here is that I'm basically computing MFCC for partitions of the audio object. This returns a 12 coefficient per partition. And I'm basically showing a matrix that every column of it is one MFCC vector of the audio objects. I can take the same thing and compare every MFCC of every partition to all the other partitions to get some kind of a repeated pattern. What's the similarity over time of the signal to itself at different times? And this becomes some kind of a signature for the audio object. And as you see, we didn't have to implement all of these because a lot of these capabilities just came with the rest of Mathematica. We just had to create some basic audio-specific analysis, and the rest comes for free. And then there are a lot of other, as I said, audio-specific functions. In this case, the same generated audio object is being reverbed. We're adding a reverb effect to it so that it sounds like you're sitting in a big church, bigger space and so forth. There is one talk this afternoon, which it's a workshop actually, talks about details of audio object. If you're already excited, you want to learn about details of what kinds of data types, how efficient and so forth. That's the 1 hour talk that gives you the hands-on experience of working with the audio object. More application-oriented talks are going to be tomorrow morning. Audio effects is more going to be just fun things you can do and transformations you can apply to your audio signals. And then we have audio synthesis and audio analysis right after each other, I think in the same room actually. So just so that I can get to the end of this talk, I should stop there. In the signal domain, there was not much we added, but there is a very powerful dynamic time warping analysis that is used in fact, audio analysis very much, in gesture analysis and so forth, the variants of it. And okay, I should start evaluating. Some of these need internet connectivity. The thing that time warping distance does, it tries to get two sequences and align them over time. So saying that time 1 of signal 1 corresponds to time t of signal 2 and so forth. And so tries to find an alignment between two sequences. This particular example tries to get, I think, 3 months of stock data of HP compared to historic data over 5 years of HP to try to find what's the closest signal over the past 5 years to this data. And so we get the times that from August to December of 2013, it seems like that data is going to be closest to what we see from the first 3 months of 2016. And what we're doing, as a very naive, simple prediction, we can get the next 30 days after that period that we find the best match in the historic data, and just add it to the current data and somehow have a very naive prediction of what can be the next coming, what can be the stock price in the next 30 days or so. As I say, there are some variants of time warping data, time warping correspondence and distance. Canonical time warping is a very practical, useful version of it. What it does is that the benefits of it over the regular dynamic time warping that is new in the recent version is that, first of all, it can compare data sets that are completely different in dimension and space. So in this case, I have two data sets, one in 3D, one in 2D, and I can still go ahead and run canonical time warping. And this is the distance that you get with canonical time warping of the data that I had first, which is basically just a projection of the XY with some random movement. And then you see the distance that it returns is 1.1. And then with some completely different data, you get a larger distance. So as I say, you can get data that are not necessarily coming from the same space, same input, and then compare them using this canonical time warping. The thing it does, it actually does a transformation to the input data so that they come to the same space so that they're comparable. It's using canonical correlation analysis and so forth. Details, if you want to read about it, we have some details in the documentation and a lot, of course, on the web. It is actually used a lot in computer vision for gesture analysis and so forth. One of the properties that canonical time warping has is that it's translation invariant, it's scale invariant, and rotation invariant. And as an example, I'm getting polygon data from some countries and compute the distances between the shapes of those polygons of those countries, and then get kind of a matrix block visualization of similarity between those country shapes. And what this does, it doesn't care if one country is significantly larger than the other one, or if the shapes are slightly rotated. It basically sees how similar they are, removing all of those scale, as I said, translation and rotation properties of them. There has been extensions to time series analysis. There is actually another talk tomorrow that goes over the advancements of time series processing, but things that can be done just as an instance. I get an audio signal. I compute the RMS amplitude, which is basically a measure of the loudness, over a very small or a fairly small partition size. I get 95 samples out of it, and I compute something else, some other property, doesn't really matter what it is. I'm doing spectral flatness here, on a larger partition size and get only 10 samples back. And I want to do an analysis on this audio object that requires combining these two time series. And as Stephen actually showed it last night as well, I can just do something like T1 over 10 plus 2 times T2, if that's the measure I want to compare. And Mathematica doesn't care if you have different timestamps and different steps between the data samples and the time series. It's all very just integrated. It resamples appropriately so that you can compare time series that are not structurally exactly the same. Okay, what's new in the image domain? Last year I talked about us starting to look into different verticals. We have already had some capabilities for computational photography. More has come since last year to Mathematica. We are starting to look at more practical applications of video processing. I should say we are still at the beginning of it. It's just a start, but especially with all the other capabilities, including the neural networks, I think a lot is going to be possible in Mathematica. Just like looking at large audio object, we have started looking at large image data. And so again, I would say we are at the beginning. There are some framework bottlenecks that we have to fix in order to really have a zippy, efficient, large image support in Mathematica, but we are trying to work our way towards those problems and solve them to give access to large image analysis and processing to all of our users. And integration with computational geometry, which is not a very far field from image analysis, simply gives us capability of getting an image, moving it to the geometry domain, getting a mesh out of it, do some processing in the mesh domain, and if necessary, bring it back to the image domain. If not, just finish the analysis over there. So these kinds of bridges between different domains of capabilities in Mathematica is becoming more and more needed from our user base, and we are basically trying to address more of them. Let's start very simple. One of the things that was lacking in the previous version of highlight image was actually the use of extended syntax that we have for graphics representation in Mathematica. What we have done recently is that we basically allow all of the graphics primitive in the syntax of highlight image. So you have an image, you want to highlight the detected face, you can just use the graphics directives and language to specify what you want to do with it, specify the face form, add more features, like I have the purple face with the green border around it, some yellow edges, and some red corners. All of it is just becoming more natural, more easy to happen. And then this one is actually using a 3-argument form of highlight image where we specify what we want to happen to the background of the image. Or you can just put anything you want to highlight the detected object. So this is basically going to come in many places, so I showed it first. But going back to the computational photography, we have added some specific capabilities like color balancing. This one is very useful to remove or add color cast. In this case, we are showing a few examples of underwater photography. And in most cases, we are basically not specifying what kind of a color we want to remove, what's the cast that is in the image that we would like to remove. The algorithm itself is trying to detect what is the imbalance in the image and trying to remove that. So a couple of examples that we are trying to take the image, detect the cast, remove it. Another thing in that domain that we added, well, basically this is the same thing. We want to map the same function, color balance, but we want to map a white to a given temperature, which kind of simulates the time of the day going from early in the morning to later in the day. Color tone mapping is another field that a lot of people, especially doing HDR photography, would be interested in. I'm here showing a very basic, or not basic, but automatic choice of Mathematica for doing tone mapping. The concept of HDR is that basically you would like to acquire more data, and then most of the time your data ends up being out of range, not displayable on a screen like a monitor or a projector. So the purpose is that you would try to non-linearly move the data in the bins that you have, basically 0 to 255, that you have to display the RGB image, and then get more of the image that was not visible in the original captured HDR on a display that is not high dynamic range. A lot of other capabilities, again, geared towards photography. This example shows the problem of whether I should use flash or not when I'm doing the photography, because if you do use flash, you often change the color of the object you're looking at. If you don't use it, you get the noise. This is the no flash one with the noise. This is the one with the flash. Looking pink, and there are capabilities like this guided filter that takes the structure of the non-noisy image and then moves the color of the noisy image to it, so that you kind of get closer to the actual representation of your image. Photo stacking is another thing. I think we showed a version of it last year. Here I'm opening a bunch of images that were acquired in using different focuses of the object, and performing some focus stacking. Again, our default choice of method and parameters and so forth. But as you see in the animation, there are different parts in focus of the image, and then you would really like to get all of those in focusness in place. In fact, this doesn't have only applications in photography. It has a lot of applications in microscopy. We have a demo downstairs showing some examples with the actual microscope sitting there that uses this. Metadata support was something we were talking about as well last year. This is released in Mathematica 11 and fairly complete. If you see anything that doesn't work, it's probably a bug. Just let us know. But in this example, we have a bunch of images from a trip, and what we would like to do is to basically just simply analyze it. We have a better support for importing EXIF, XMP, and IPTC, and now we have a capability to modify them and export them to the file. So what you see here is not quite correct. What has happened there? Oh. Sorry? Okay, let's give it another try. The geopositions should not have these select stuff in them. Okay, don't know what's going on. Let's move on. I don't think I have enough time to go over all of these. But despite the select okay, so we're getting rid of the altitude anyway, so we didn't need the altitude. But what we're doing is that we're computing again something from the geo capabilities and trying to compute the travel distance that the person has acquired these set of images, have potentially walked to get all of these images, sorting based on time. So we use the time to sort the images using the geoposition to compute or estimate the travel time. And again, there is more of it in the talk later today called image collections, where we are actually putting some focus into metadata analysis in combination with the rest of Mathematica. This is just a geoplot of the positions, and yeah, this probably should have not just been here. All right, let's see. Large images. Again, I think we showed a version of dynamic image last year. The purpose of this new function is to have access to images that are fairly large. This one is not, still I think fits into my memory, if it does, in fact, I know, into the memory. Image size. 9,000 by 4,000 roughly, but often people have gigapixel size images that really don't fit into the memory, and you need some kind of a handle to it to visualize and display the data and, well, eventually process it, which is not yet available. But this little GUI gives us a very easy way of navigating the image and see the details that is happening in the image. And I think next, actually, I may be able to show exactly. OK, so what we are building on top of dynamic image, which again should be probably happening easier than even that many lines of code, is active measurements of anything that you have in your image. For instance, in this particular case, I can try to zoom into a given part of this microscopy image, move around, focus on the object of interest, move to the center, adjust the parameter to somehow get an estimate of the size of the particular object that you're interested in. So these kinds of things come a lot, again, both in photography, microscopy, and so forth. And the new function dynamic image not only allows us to view large images, but also lets us do these kinds of interactive analysis and so forth. And then more next, we have this demo that shows side-by-side comparison of images. This is also a set of two large images, a radar and regular photography satellite imaging of Venice. And then you see that if I want to zoom into some part of the image, it's not that difficult given that your screen is limited to how many pixels you have on it. You typically don't have as many pixels as you want to have to see all the details. Here we are putting two dynamic images side by side, and changing control in one of them is basically affecting both of them by using all of the dynamic capabilities. And you can see that we can zoom into the part of the interest and see streets and valleys and roads and rivers, whatever is interesting. I think I have to go just a bit faster. Optical flow analysis has got added to version 11 as well. Here I have a set of images that are showing some windmills rotating. What we have done in Mathematica 11 is just this one function image displacement, which tries to find displacement of pixel values. Sorry for the poor resolution image. I should have used a bigger one. That tries to show where every XY pixel in image 1 is moving in image 2. So finding correspondences between all pixels in one image and the one after it. And then again, the thing I'm repeating myself, the beauty of all of this that we're doing is the rest of Mathematica that gives us a lot of nice capabilities. For instance, you can get that displacement data for all of the images in that sequence and compute the curl on that, which gives you a good estimation of rotation. And then, this is just getting the mean of all of the rotations or curls over the sequence of images, do some blurring to get rid of the noise, and then highlight where you had most of the rotation happening in the image. This is going to be probably a quick little demo if it works. We're using some dynamic capabilities, current image, and exactly the same technology I showed above. And since I'm running out of time, I would like to move the time a bit back to save myself another 10 minutes or so. Good, I have more time now. OK. Right. A lot of actually, again, gesture analysis, motion analysis, activity analysis is happening using these kinds of technology in actual real world. And then again, a lot of it is becoming more and more easy to do. Talking about bridges, we have this image to geometry conversion. Here I'm getting an image of the Great Salt Lake, binarizing it based on some little marker that I specified in that little image to get the contour or the shape of the lake. And then we have this new function image mesh that I can run and convert it to an actual mesh. I can triangulate it with any mesh size that, or the cell size that I would like to have. And then we can, I think Steven showed France and talked about, looking at it as a, top of a drum and seeing what are the oscillations. This is practically the same thing, but since this is a lake, you can think of actual waves of the water moving back and forth on the lake. So if you want to do simulations like that, this is an instance of where you would like to take the imagery, the satellite imagery, convert it to the mesh domain, do your processing there, and then basically take it from there. More of these kinds of bridges are going to be coming. I think I'll skip this one. It's a bit more. Well, maybe I'll just quickly run it. Don't talk about it much. We have 3 images of an object that were acquired, and what we are trying to do is that we are trying to do some kind of a multi-view reconstruction to get a 3D version of the little statue that we have acquired. Using the same image displacement, we are basically computing an estimated depth map, and then using image mesh, which is here, we are trying to find a structure of the object, and then we are basically combining them to get a 3D representation of the statue. Limited to what you acquired with the 3 images. With more images, you get more accurate. And this one, I think, is just a 2D version. And this is with the texture of one of the 3 images acquired. A bit more intensive for my laptop to run. But you basically get the same 3D graphics that I had above with the texture on top of it. Maybe I should have not done it, but I have 10 more minutes, right? It's just 11:20 now. Okay. I can think what I had in slide number 14, 15, and 16. Neural network stuff, nice stuff. Again, there are a lot of nice other talks. How can I kill this? Oh, okay, came back. All right, so worth rotating it now that we have it. Okay. Yeah, deep neural network, I actually didn't add a more elaborate example than what Steven showed last night. This is the classic MNIST. Stores a whole bunch of handwritten digits, and people have tried to recognize the handwritten digit for so many decades now with different algorithms, and now deep neural network is actually lifting the bar to a better threshold and better precision. So what I keep telling people as I talk about image processing with conjunction of deep neural network is that this with Mathematica is not rocket science anymore. Some people come to it and think like maybe it's difficult, maybe I don't want to still touch it, but really all it is that you just have a network, just a chain or a graph of operations that are as simple as dot products and convolutions, nothing complicated or beyond our thinking. At least most of us have math background. And once you have all of those operations figured out, which there are a lot of models for what kind of neural networks are going to work for what kinds of problems, there are actually a lot of curated data on what networks to use. In Mathematica, you just get the training set called NetTrain. It just does the job. And just like last night, I'll stop it at some point and run it on the sample data. Well, the 4 is detected as 9, but I guess with that. Sebastian, who developed the neural network framework, is talking about details of the neural network on Friday morning. And then later in the day, Matthias from the image processing team is going to be showing some applications for image analysis, identification, and processing using the neural network. So if that's something that interests you. OK, I'm almost done. What's next? A lot more audio, image, signal. One cool thing I wanted to show that I can't show in this version of Mathematica that I'm running, that I should have shown with audio, in fact, I showed in slide 2, that you can just get an audio object, do things like 2 plus audio divided by 10 and so forth. Very naive, very, very simply. It's once you do it, when you do it once, it seems like you should have been able to do it forever. But this is something actually we can't do for images in the version that is released. But that's something that should be able this is, if I actually quickly get my X here and my nightly build, I should be able to run that. But as I said, a lot more microscopy is coming. Astronomy, we're looking at fits and trying to get a lot more applications. This is actually neat. Let me quickly run it. Sorry for the next presenter. There is a demo that is happening downstairs for microscopy. I really want to encourage you guys to go there. So, okay, so this is what I do. I just compute some hyperbolic tangents and cosine and gradient and combine them. You get an effect. This may look cute in this presentation, but often you want to do a lot of actual analysis, like get the gradient, combine it with Laplacian of the image and so forth to really find some centers of the nuclei of the blah blah kinds of cells that your whole research is on. So these kind of things are just becoming a lot more immediate in Mathematica to program and a lot more efficient because you just work on the byte data or whatever kind of packed data that you have stored in the image object. No need to expand it to actual 64-bit real data and blow out the memory, and efficiency gets worse and so forth. So I guess that's about it. We had just released new Mathematica 11, so there are a lot of neat examples on marketing pages. Some of these that are showed are from there. So anything you want to explore on the website, and you can find me or others from the team during the next 3 days. Thank you.